Okay.
Our next speaker is Petr Lisonek. He's from Fraser University, Canada. He's going to talk about constructions of APN permutations. Okay.
Thank you. The Control L, oh, it does work inside Zoom. Sometimes it does not. Okay, well, thank you. I'd like to thank the organizers for inviting me to this very interesting session. Good afternoon, everyone. I'd like to speak about APN permutations. And this is joint work with my master's student, Benjamin Chase, here at Simon Fraser. So I'll start with explaining what the APN permutations are and why we are interested in them. And then there'll be two parts to the talk. In the first part, which deals with Voice-zero spaces of APN functions, we will be actually able to construct a lot of new APN permutations, and this is desired for cryptographic purposes. In the second part, we'll be investigating so-called Kim-type APN functions, which is a family that was introduced a long time ago. And there we'll also have a major result. However, that one will be negative in the sense that there is no new APN permutations of that type. So both is interesting from the point of view of classifying or constructing APN permutations. The first part is a positive result, and the second part is a negative result. So first, about the APN functions. So function is almost perfect nonlinear, or APN, if this equation has at most two solutions. We are considering this function f mapping field of order 2 to n to itself. I know I could have written plus instead of the minus, but I'd like to emphasize that this is really, we are thinking of this as a differential, so that's why the minus is there. More generally, if there is, say, at most four solutions, we would call the function differentially four uniform functions. In characteristic 2, we can only achieve even values, obviously, because if x is solution, then x plus a is also a solution to this equation. But the best we can achieve, therefore, is 2 uniform, and those have this special name, almost perfect nonlinear. This is a session of finite fields, so we'll be using the finite fields a lot. For the concept of the APN function, the field is not required. You can use other additive groups like the vector spaces, for example. You don't need necessarily the multiplication of the field. And there are some geometry constructions, or you might even use other groups than these. So why do we care about these functions? They protect block ciphers and other cryptographic tools against what's called the differential crypt analysis attack. So the number of the solutions to this, what we could call a difference equation, that's why it's written with a minus, is small for any a and b, and therefore the differential crypt analysis is very hard for these ciphers, and that's one of the main attacks these days against block ciphers. So that's why the APN functions are important in the design of block ciphers. Now, in certain designs of block ciphers, which are called as substitution permutation networks, it is important that the function is not only APN or has low differential uniformity, but that the function is also a permutation. There is an S box inside the block cipher. It's a key component of the block cipher. Is the only non-linear component of the cipher. And so if we use the APN function to create the S box, if the S boxes are invertible, so there are permutations of the field, then we can use the same circuit for encryption and decryption. Essentially, there are some little tweaks, but essentially we don't need an extra device to decrypt. So the device that we use to encrypt can be also used to decrypt if the APN function is a permutation. So that's why APN permutations are so interesting in cryptography. So there are some examples. X cube is APN for in all dimensions, but it's only a permutation if n is odd. Vice versa, the field inverse function is APN if and only if n is odd, although it's a permutation for all n. So when we look for APN permutations, it's often easy to achieve one of the goals. We know lots of APN functions, we know lots of permutation polynomials, of course, but to achieve both at the same time, the APNS and the permutation turns out to be quite a hard task. So there are, in terms of what we know about the APN functions, there are infinite classes known. Of course, you know, every functional finite field can be described as polynomials. So we start with polynomials with few terms. So the monomials are all classified, the infinite families, when they produce APN functions. There's also several multinomial families of APN functions. They'll have typically about 4 or 6 terms. Turns out the question is very different for depending on the parity of n. So as you can see just from the first slide, first line, in all dimensions, the answer is easy. Obviously, we do have these APN permutations. But in the even dimension, the question is much harder and it's unresolved for even dimensions greater than 6. For any function from the field 2 to n2 itself, we define the so-called Walsh transform. It's probably a well-known transform, so I won't spend much time on it. It's used also in studying of linearity or rather non-linearity of functions, which is the other important aspect of cryptographic functions that has to deal with the linear cryptanalysis. That's where the Walsh coefficients occur a lot. But here we actually use them to construct APN permutations. And our interest is in those pairs AB where the Walsh coefficient is 0. So if we can make a whole vector space of such Walsh zeros, a space of dimension n, where each element except the origin is a Walsh zero for the given function f, then we call this a Walsh zero space or WZ space of that function f. Those Walsh zero spaces occurred implicitly earlier in the literature, but they have been explicitly used as such only, I would say, recently in the last few years, but the importance was recognized. So there's, for example, a work by Anne Canto and Leo Perrin, where they associate these Walsh zero spaces that I just defined with the partitioning of CCZ classes of a function to extended equivalent classes. These are two kinds of equivalences on the cryptographic function. CCZ means Karle, Sharp, and Zinoviev. The EA means extended affine equivalence. So you can think of the affine equivalence as applying an affine transform on the input on the function and also on the output of the function. And also you can add an affine function. So all these transformations will not change the differential properties of your function, and therefore the EA equivalence means that the two functions are kind of trivially related in that sense. So these zero spaces that I just defined, examples have been obtained numerically. So for example, this construction by Dillon, it's purely numeric. There are no theoretical considerations of why it works, or very little, I would say. So it's mostly computational, the paper. And as far as I know, in this work, we are providing the first, I would say, pen and paper, so computer-free constructions of non-trivial War-zero spaces. There are always some trivial ones. We'll get to that shortly. So one more thing that I need about the War-zero spaces, I need not just the spaces themselves, though those are already interesting, and that's the work of Canto and Perrin, where they show that their importance. But we, for our work, also need actually pairs of such spaces that intersect trivially. That means only at the origin, and then we'll call them a TI pair for trivially intersecting pair. So if I have such a trivially intersecting pair of two War-zero spaces, then the function for which these are the War-zero spaces is CCZ equivalent to a permutation, and that's if and only if. So you can start with an arbitrary function. You can study its War-zero space. If you can find two of them that intersect trivially, you can actually construct a permutation CCZ equivalent. So the construction amounts to rather simple linear algebra. The CCZ equivalence, I did not define it, but it preserves many important cryptographic properties. In particular, it preserves APN property. So in other words, if your function f already is APN, and on top of that you can find this TI pair, then you can actually, this is a vehicle that lets you construct an APN permutation then, because the CZ equivalence will preserve the APNS, and the permutation will be constructed based on the TI pair of WZ spaces. So this was what they did numerically. Dillon and his students was presented at FQ9 conference. Kim, I believe, is the first name of one of the three students that worked with him, and that's why the function f that they used in this construction is called a Kim function. That will be the second part of the talk. As I said, they only use the WZ spaces implicitly. They don't even, they have an equivalent presentation in terms of binary linear codes, but it's implicit in there. So we said it's good if we can find these TI pairs of WZ spaces. So first, as I said, we have the first computer-free constructions of WZ spaces. So we'll construct them for the gold functions. This is probably the best or most known, most studied function class of APN functions. This is based on the characterization by Gold from 1968. These are, of course, also relevant to other areas such as sequences with low cross correlations. It's the same mathematics behind. So these Gold functions possess these two trivial WZ spaces. The first one is possessed by every function, and the second one is possessed by every permutation. And Gold implicitly proves this test when a pair of elements AB is above 0 for this Gold function, and it is when this trace is 0. So I'll call this Gold test. So here is what our theoretical constructions of these WZ spaces look like. So they have typically this form that it's a set of pairs of elements, and there's usually some conditions on the component. There is scaling possible also, of course, so that's the mu is the scaling, so we can make many spaces of the same in one family, I would say. It's not, a direct scaling by mu, right? It's of course less trivial. So how do we prove these constructions? Well, we show firstly the additive closure, that it's actually in a space, the set. That usually is done because the constructions typically involve linear forms. You see we have here condition that's linear, right, in A and B. So that's how the additive closure is shown. We need that the dimension is n. So for that, we typically count elements. Here it would have to be counting the number of solutions to this equation. So show there is 2 to n elements in the set, and verify that each element is above 0. And for that, we use that Gold test from the previous slide. So that involved the trace of an expression in A and B. So we just plug this into that trace condition and do some finite field algebra to verify that the trace is 0 as it should be. We also have constructions that are based on spaces, on vector spaces of with special properties. So when I have a vector space S, I can take the set of all these elements. You see, this is the second term in the trace test of Gold, right? This in general will not have any particular structure, this set, but it could happen, if I'm very lucky, it could happen that this set is also an additive subspace. And if I'm that lucky that it happens, I call it an I compatible for the I that occurs in there. So there are some obvious I compatible spaces. These 3, I can scale them by a scalar. So those are, I would say trivial examples, of course, these in the green box. There's a non-trivial example when 3 divides n, in which case the subfield F8 provides interesting examples, because in F8, each subspace actually is 1 compatible and also 2 compatible, because if you actually figure out what those powers in the definition, so these powers to -1 over 2 to I plus 1, and they are for I equal 1, it's -1/3, for I equal 2, it's -1/5, and those are actually x squared and x4 and x to the 4th on F8, and these are linear functions, and therefore I do get a vector space, right, after doing the powering. Now, we don't know any other examples at this point. So an interesting problem we'd like to propose is if there do exist any other I compatible subspaces of F2 to N. because we have a construction based on these I-compatible subspaces. So this is a product construction. So I showed an example of a direct construction of WZ space. This is a type of product construction. So you take an I-compatible subspace S, and then what you do here is essentially you take the trace dual, right, of this set, right, because this operation, this exponentiation operation, is a permutation. In this set, you'll have as many elements as in S, right? So in other words, if you take a span of this set, the dimension will be at least the dimension of S, right? And then to achieve the dimension n overall, because we didn't do the product construction X cross S to obtain the WZ space, we need the dimension of X be complementary to dimension of S, right? And so that's the highest possible dimension that X can have. And for that, we need these things to be exactly aligned in a vector space. So that's where the compatibility condition is needed. So that's an example of a product construction of these WZ spaces. So I also need for doing the Dillon type construction, we also need these trivially intersecting pairs. So this now becomes quite technical, the formula. So I just want to show that we have such results. So we have lots of constructions where we have these computer-free constructions of trivially intersecting pairs. So to summarize this first part, the theoretical constructions of these WZ spaces that we gave on the previous slides, we verified they are exhaustive in odd dimensions, at least up to 9. And we have constructed many new APN permutations, new in the sense that they are not EA equivalent to the gold functions or their inverses. We have still lots of computations ongoing about that. To show that they are not EA equivalent, affine equivalent, extended affine equivalent, we can just compute some simple invariants of the functions like an algebraic degree. Those are preserved by EA, and therefore, if they are different, have different values, then we know that our functions are not affine equivalent to the gold functions or inverses. Okay, so I see I'm running out of time, so I'll just very quickly say in a few sentences. So this was a positive result in the sense that we constructed many new APN permutations in odd dimensions. I want to admit that, you know, of course, the hard task is the even dimension, but even in the odd dimensions, it's good to have as many APN permutations available as possible, because when you design ciphers, there is lots of other properties that these functions have to satisfy, right? There's the linearity and the avalanche criteria and lots of other criteria. So therefore, it's good to have a good pool of APN permutations to choose from, so we can assess them with the other criteria. So it was a positive result because we had these constructions. So the second part, which I'll do really very quickly, is a kind of negative result, which in some sense closes a certain, I would say, sequence of papers or investigations in a certain direction. So I mentioned before this Dillon's construction of the permutation in dimension 6, APN permutation. And that was based on a special function, which is called Kim function. And then they did the CCA transformation that I described before, got an APN permutation. So of course, there was interest whether this can be generalized in higher dimensions. So people were looking at the form of this trinomial that was used initially. Turned out that you can have a quadrinomial, so one more term. So there's the general form. So people are wondering, could this actually be used? Could a function in this form be CCA equivalent to a permutation? And in our work, we used a characterization, which is just a year ago published by Lily, Halazad, and Q, when these functions actually are APN. They have conditions which are kind of algebraic and trace conditions when such a function is APN. And we also had with Faruk Gologlu and Dasha Krasnayova from Charles University from Prague, we had previously also approved when these functions are APN or characterization, but restricted to the coefficients AI being in the small field. So these are, it's even dimension. So the function is defined to be mapping from Q squared to Q squared, or 2 to 2m to 2m. So we originally we had a result when the coefficients were in the small field, in the subfield FQ, and in that case we show that if the function is APN, it must be affine equivalent to the code function. So there's nothing new there. And in this work with my student Ben Chase, we combined these two results that I just mentioned. And we showed that now the statement holds in when you allow the coefficients in the larger field. So the function is mapping from Q squared to Q squared, and the coefficients also can be in Q squared. So that's the most general form of these Kim type functions that were hoped to provide possibly APN permutations. And we showed that although there's a very general family, you have 3 different coefficients from the large field that you can put in. We show that if such a function is APN, then it is a known function in the sense that it's affine equivalent to one of these code functions. So I'll post the slides. I think I'm out of time, so I'll stop here. And if you are interested in the technical details of this, then you can look them up in the slides. And thank you for your attention. Thank you.
Thank you very much.